Okay, let's get started. So, first of all, I want to talk a little about the final exam. So the final exam, the date and time has been well, the time has been determined like a while ago. Now the location also has been given. So the time is going to be December 10th, 11:15 to 1:45. This is location is Javits lecture hall, room 101. Okay, it's not a classroom. It's going to be the Javits the lecture hall. Okay, 101 is a big room, and both in session and online we're gonna take in the final exam together. Okay, it's a big room. Should be able to hold everybody. Now then for the December 8th, okay, December 8th, there's then December 8th, no class, but I will hold office hours. Okay? That means on that day, a regular class time will be used as office hours. So the office hour are going to run from 9:30 to 12. But I will do it office hour via Zoom. Okay, then because then people can. I feel like a Zoom is probably easier for the class. Like you can come and go. You don't need to go to my office. You can like anywhere, any places. Like if you have any question, you can just jump into Zoom. So I feel that's probably easier for the class. So that's then on December 8th we don't have regular class. Then we'll have like a 3-hour office hour session for the class. I do have a little bit of lecture left for the which is about the bootstrap. So big data bootstrap, but I feel like because 10th is our final exam day. Then if I taught anything like new things on 8th, you probably won't be able to focus really on that. So I decided. So then there's no new stuff on the 8th. Okay, he just review like office hours. But I will post the lecture notes about the big data bootstrapping, the notes on the Brightspace later. So you can review them when you have time. But that's will not be covered in the final exam. Okay, so that's this is a little bit about schedule. I will leave this is on the. I will leave this information on Blackboard for today's class because people come in late. That's the question. Oh, yeah. Then for the final projects, every group now already have I want to share my whole screen, so I don't need to switch back and forth. So now every group has the topic, choose their topics. Here are the order of the final presentation. Is mainly just grouping by like more like similar items, and then it's not that rigorous. So if you like I mean this is unless you have a very good reason you want to switch the order, like some group in the December 1st you want to go to December 3rd, but other than unless you have very special reason. Okay, so this is the order. We will buy the order of this to for the presentation. There are a couple questions asked me for the final projects. I think I already kind of mentioned in the when I was doing that, but I just want to reiterate this is for first thing is how many people should give in the presentation. I think I already mentioned that. It's basically it's not possible for everybody to give a presentation. Each presentation roughly should last about like 15 minutes. We will have 5 Yeah. So the class, each class, so we're going to use the December 1st and December 3rd class time for the presentation, right? So the class time is 80 minutes in total. So we're going to have 5 presentation per class. That means each class getting about like a 16 minute of time, okay, for presentation, including the presentation and also the QA. So that's 16 minutes. It should be the time, and including like you get it up, then setting up, so they'll leave like 1 minute buffer, which means your presentation should be roughly around 15 minutes. Okay, that's to be the maximum. Which means if you each group has about 8 to 10 per people, so then it's, if everybody speak, then each person is gonna get like 1 and 1.5 minutes. So that's it's not necessarily too short. So what I decided is for this year, what we're gonna do is we're gonna you each group, okay, you can choose like up to 4 presenters. Okay, so you should be using like 4 presenters for the presentation. I mean, but it shouldn't just be 1 or 2. Okay, it's better to be like somewhere between like four presenters. I think that's a good number. So each one you talk about like 3 to 5 minutes. That's about the who to present. Then, but when you do the presentation, okay, everybody should be up. Okay, should come up to the and then the question can be asked to any one of the members. Okay, so the presentation can be done by like 4 people. But if I ask a question, then based on your presentation, right? So you can ask a question, and the question can be addressed to any one of them, one of your group members. So although for the people may not be like doing a presentation, but still you need to be familiar with all the slides information. Then in case you're being asked a question, you'll be prepared to answer them. Okay, so that's about presentation. Then second thing is asking about like is MPI4Pi required for each presentation? Absolutely required. Now for example, like for the group 3, right? Spark PySpark. Obviously, it's a Spark. This is a system. Is a big data platform. So you can using Spark or PySpark. For some of them, if you can using the MPI, most of them, okay, should be able to use MPI4Pi for the implementation. But if you feel like you want to do Spark, for example, you want to do Spark, or you want to do using Hadoop system for implementation, that's also fine. The only thing is we didn't really cover like Sparks in details, right, in this class. So if you Spark, then you have to make it in your code to be like easy. Then you really have to explain things, okay? Because for the MPI4Pi, the class are used it, so it's easier for class to follow up. But if you decided to using something else like different from MPI4Pi, just make sure the class can follow you guys the presentation or like the execution. Because at the end of the day, your code you gotta be shared to the whole class. So this brings up to the third point. Should you submit like a script separately? So that's if for some of the projects your code may be very small. In that case, you can choose to including your scripts into your say presentation slides as a sort of like a appendix. Then you don't need your actual file. But if your code base is kind of large, then a separate file would be desirable. So what I want to do is I want to everybody share your code with the class, and then I will those may all be distributed class as well. So in that case, in the future, if you see, for example, like a recommended system, then or some kind of like the retail inventory management system, right? If you in the future you encounter such problem, you you have something to start with. Okay, that's the idea. So it's so you should be prepared to have your script ready one way or other. Okay, so that's the point. And another thing asking about the report. I don't need like a special report to the like writing a separate PDF file for the report. Your presentation slides are your reports. Okay, so you should include enough details in the presentation slides, which is, as I said, it's gonna serve your report. It should have like in detailed the message for people to follow. Okay, to go through the slides. But of course, when you present, you'll be writing a lot of text, and you don't have to go through every details. But you can just go through the key points. So then in this case, I don't want to give you like as extra burden to write another like a 10-page PDF. I think that's it's not necessary. Everything should be already in the final presentation. Okay, so that's the clarification I want to give for the final projects. Any other comments or any other question about the final projects? All right, so if you don't have any question from the online session? All right, so if you guys don't have no question on the final exam and the final exam, then a final project and a final exam, then we'll continue our the class notes. So in the last class we start talk about the soft margin classification for the SVM, right? The soft margin classification essentially the idea is to introduce the idea like allow the points to be misclassified, okay, to be on the other group instead of like you have two perfect separate group. This is kind of impractical in the real world. So we allow the some points to be on the wrong side. Then the solution to that is we introduce another slack variable called psi. This slack variable basically is some quantity, some positive quantity, which is say when the points can be the distance to the separator is bigger than equal to 1 minus psi I. So which means if it's if your points is on the right at the right side, okay, then your psi essentially is 0. That means there's no slack the value attached to that. But if your points is on the wrong side, then this psi can be okay. This psi can be on the this side can be on the other side. Now there's a question they're asking is can this psi I to be like can this side to be like, for example, like half? Okay. Is this possible? I think that's a good question. This is a question was asked after class. It's the when we define this psi, should this psi to because the psi when the psi is half, that's basically see this blue dots is going to be somewhere in between of the separator and the boundary. Okay. Now if the psi is bigger than 1, that means you allow your points to cross separator to on the other side, okay, to the other side. Now, then the question is, can this blue point, for example, the blue point, be somewhere in this margin, okay, in the margin region? So if it's be like it's less than 1, so then it's actually I say it's a good question because if it's a perfect separable, okay, if it's perfect separable, there shouldn't be any points between the separator and the boundary, right? Because if there's such a point, you just narrow margin, right? So, but however, when you allow this to be cross the other side, now you remember the separator is not only determined by blue group, okay? The separator, or in other words, the boundary or the separator is defined by both group, okay? By both group, it could be on both the red points and the blue points. So if there's a red point, say if it's very far away from the separator, it can bring this separator into this region. So therefore, all there's a point due to here. So it is possible, okay, it is possible the boundary is somewhat beyond this is a there are some points actually be between this two lines, okay? So this is it's possible. And this is actually is a pretty subtle point, okay? I just want to I want to clarify a little bit. So when we having this is the so like soft margin classification, the problem essentially is we want to minimize this is half the beta transpose beta plus the C times the summation of the slack values, the sum of psi I, subject to the yi times the distance, right? Distance of the each point is bigger than or equal to 1 minus psi I, and the psi I has to be positive, right? Because psi I is a distance on the wrong side. So in this case, we have in parameter, additional parameter C. Okay, this is C is view. This C is actually the penalty to the psi I. How large this is you allow your psi to be, right? The larger the C, say for example, like C is infinity. Okay, C is infinity. Then your psi essentially has to be equal to 0, right? Because then any point like a different psi I, as long as you're choosing some value, then you will not be able to if any for the psi is different from 0, then this term is infinity, so you cannot minimize it. So then the minimization has to come down to the this psi equal to 0. If psi is equal to 0, that means it's degenerating to the original the SVM. Now, when the psi is other values, because then if we this also can be seen from the dual problem, right? So the dual problem, as I didn't go through it, I asked you guys to go back to like check for the dual formation. I don't know how many have you done this. If you haven't done it, okay, I strongly suggest you to do that. So if you check in the dual form of the dual problem, or this is a primary problem within the psi I in there, you can say the dual problem, the formulation are almost identical to the original problem. Okay, original SVM with perfect separation. The only difference is now your alpha I is bounded, has upper bound C. Okay, upper bound C. Now, if your C is equal to infinity, then that essentially means your alpha has no bound, which is go back to the original form, right? So this is the similar what we have down here is infinity. Basically, psi has to all be 0. You can see that from the dual form as well. So the amazing thing for the dual form is neither slack variable psi I or their multiplier appear in this dual problem. Okay, they are essentially gone. So you're solving this is a soft margin classification algorithm-wise. If you're using this dual problem, it does not increase in a lot of complexity. Okay, it's just the only thing is to have one extra constraint, which is alpha I less than equal to C, or not one is extra constraint on this alpha I's. So yeah. 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 No, this is for the perfect separation margin. Okay, this is when you're having the points perfect separable. When it's not perfect, we assume its distance is 1 minus psi. Okay, so when you allow this is a point to be away on the wrong side, then the distance is 1 minus psi, not 1 anymore. Okay, that's this is where the psi come into play. So if you have two groups that are perfect separable, okay, there's no such thing. Even have the psi, then if you can also introduce this so when your psi is soft margin classification can also be applied to the perfect separable cases, right? So in these cases, there's no psi is gonna be all the psi are just essentially just be 0. Okay, there's no half. So that's you can see in here, everybody has the bigger than 1. The minimal distance is 1. So that's this is for the perfect separable case. But in the soft margin, we know this is why we have this is the distance is going to be 1 minus I. It's different from every point. Okay, yeah.
Just because I'm not quite wrapping my head around, the graphically show what it means by 1 minus psi I can.
Here, this is graphic show. This is graphics. Okay. So this graph I think is actually a little misleading because this is psi I is the distance to the boundary. So this should be, so this whole thing is psi I, and this is this distance to the boundary. This is a 1 minus psi. So geographically, this just means if your points is for the blue point, okay, if your point is on the right side on the boundary, your psi will be equal to 0. Okay, that means you don't need any slack list. You don't need any slack variable. But if you are on the wrong side of the boundary, like if it's to the for the blue point is to this side, then you will need some psi I, some value to account and say this distance could be less than 1. Okay, we're allowing this distance to be less than 1, and this distance is determined by both the blue points. Like a separator in this case is going to be determined by both the blue points and the red points. Okay, so it could be it could be, therefore it could be that the blue point somewhere here. It's possible. Okay, I'm not saying it's always going to be there, but it's possible. Or the blue points can be here, or can be here.
So psi I is the value psi I.
Yeah, it's unique to each point. That's why it has a subscript to I, right? The I, that means it's for each point.
Yeah, sorry.
Yeah. And this is just basic thing is you want to say you kind of like if you psi I you can view is the budget to each point, right? Then this is a summation size like a total budget you given to each point, and this total budget cannot be too large. Okay, that's we have to minimize. This is somehow we basically give a penalty or penalize if you spend too much budget. If the psi I is too large, that basically means a lot of points is going to be on the wrong side. That means we don't allow that, right? So that means if you, for example, this line we will have a smaller psi, right? But if I draw another line, okay, say for example, if I draw a line like this, okay, then there will be a lot of this, like all this red line, all these blue points, they're going to be on the wrong side. They all carry some psi value, which is going to be denied by the algorithm. All right, so yeah, so you have then this psi is for each point. Okay, you have to pay attention to the subscript. Now again, the solution to this form, as we go through, just we did it for the Warrington form. The beta, it will be summation of alpha I y xi, and this alpha I, just as I argued before, most of alpha I they will just be zeros. Okay, they will just be zero because simply because the Lagrangian the KKT condition, right? KKT condition. So then in the most cases your points is going to be away from boundary. So you're going to have, and this is alpha I, most of them are going to be 0. So therefore beta are going to be determined by those ones on the boundary. Okay. The B is determined by only choosing a point which is the support vector, and then plug in this is the beta, and then we can basically computing the B values. Now the thing is neither beta or B are needed explicitly for the classification. Okay, are needed for the classification. So what do we have here? What do we have here is we have a problem. Okay, we have a problem. We want to maximize this is Q alpha, right? This is alpha 1 up to alpha n. So we have this Q alpha is going to be equal to half of summation. Because I want to summation of alpha I minus half of summation I from 1 to n, summation j from 1 to n, alpha I, alpha j, yi, yj of xi transpose xj, right? Subject to constraint, subject to constraint would be summation of alpha I yi equal to 0. This is alpha I is bigger than 0, less equal to C. Okay. So this is our problem. What is our solution? Okay. Our solution is saying the beta is equal to the summation alpha I yi xi. Now the prediction, okay, the prediction, which is fx equal to beta transpose x, beta transpose x plus b. Okay. Now notice here, b is equal to what? B is equal to the yi times 1 minus psi k or yk. So yk minus beta transpose xk. So beta transpose xk basically is the summation alpha I yi xi transpose times sk. Okay. Now the prediction. Okay, this is a prediction. For new point x comes in, it will be equal to this. This is going to be equal to summation of alpha I yi xi transpose x plus b. Okay, plus b. Now, if you look at the whole thing, okay, if you look at the whole thing, the original problem does not really have beta into there. Okay, so original problem, what do you have? Well, essentially, as long as you define, okay, as long as you define a relationship between xi and xj into this is the inner product, right? Xi transpose xj, this is the inner product, right? Inner product. Now, once you define this, okay, then you can make your prediction just using the same function, right? So this is function. This is going to be xi to the xj, xi transpose x into this. So if we can redefine, okay, if we redefine some form of xi, this is I kind of go through this is the original problem, but now this is even this statement is even stronger because now we are allowing the points can be on the wrong side. So this is like a general problem. So, or in another word is if we replace, okay, if we replace this xi transpose xj, this is just, you can just view some kind of function, okay, some function of xi and xj. Just so happen this fi xj is equal to the xi transpose xj, right? So if I replace this is I can define some kind of the operation on 2 points with some function f. What f is a problem? Yeah, that's okay, because I don't have f in other places. Now you can see, then when you do the prediction, all you need to do is just replace this as xi x. Right? And your b is also the b is here, is just f xi xk. Right? So if you look at this form, okay, if you look at form, there's really not the things we can prevent us to replace this xi transpose x with some function of f, which is defined f xi xj, and then we can just plug in using the same inner product, replace this function. Okay. So what this means, if we can find some function, okay, by define it in this way, this actually generalize our the sort of classifier to a new sort of like a new algorithm. And all of best of all is replacing this does not change our problem at all. Okay, does not change our problem at all, because the parameter we want to maximize is alpha. Okay, this xi, these are just their values we define. So therefore, if you make this replacement, it won't increasing the complexity of the algorithm at all. Okay, because this is just a constant. Okay, this is just some value. Then so your algorithm try to solve alpha I, alpha j is still the same. Okay, then you don't even need to change the algorithm. So this is the idea of the kernel. In just a second, I will introduce it. But so I will leave it. This is on in here. We'll come back in just a second. Before we do that, we're going to introduce, this is a nonlinear support vector machine. So, oh, exactly, the race is right here. So if I can replace this is you instead of using a function of in here, I call it a function k, right? Let me just make it k. So in that case, k stands for kernel, right? So if I can replace some function of k, then the solution is just you just replace this key xi transpose xj replaces the key xij, then the solution is going to be the same. Okay. So other optimization technique for finding RFIs are the same. So by doing this, we kind of like going back to the nonlinear SVM. But then the question is, if we do this as a separation, this is a dual problem, right? But what is the primal problem for corresponding to that? That's actually not easy to answer, okay? Because we now having a different view. In some specific case, we can go back to the primary problem, but you can see the general. That's why for the SVM, the dual problem is very important, because if you go into if you look at the origin of the primary problem, okay, it's not easy to find this kind of generalization. But if you're going on the dual problem, if you look at this form, okay, if you look at the form, then this generalization to the nonlinear SVM is become very natural. Now, then the next thing is next I want to introduce a little bit about like what are the benefit of this is a so-called nonlinear SVM. Okay, so I want to just spend like a little bit of time to include, because this kernel function is sort of like you can view it as a generic function, but what exactly it does, okay, that's still unclear, right? I try to, so next few slides is basically try to explain what is key xij, what it does, and why what are the good choice of this key. Mathematically, anything can be like any key function you plug in should work, okay? But just certain classes they can have like they can have good property. Now, that is essentially corresponding to nonlinear SVM. Okay, the idea for the nonlinear SVM is we can separate data if your data are non-separable in the lower dimension space. Okay, and if you can map your data to higher dimension, as long as you can map your data to the dimension high enough, okay, your group will become perfectly separable. Okay, so your feature space may even become like it has infinite number of dimensions. So in that case, as long as you map your data points to higher dimension, you can make your data like perfect separable. Okay. Now, we need not sometimes we need not explicitly construct new feature space. This is a point out that we're gonna see again. You're gonna see in just a second. Now I want to give you an idea why so like project higher dimension space is perfect separable. What does it mean? For example, like in the first case, right, data are linear separable. You have this is one dimensional. Your feature space is one dimensional. You have one feature, right? Now the red dots here, blue dots is on the right side. You draw a line in the middle. They're perfect separable. But if you put in a few more red dots on the to the right of the blue dots, then no matter where you draw the cut, the blue dots and the red dots, they cannot be separable. Okay. However, if we construct the additional dimension feature called x squared, right? So this is your x, this is x squared. Then by projecting your original one-dimensional data points into two-dimensional, you arbitrarily construct the additional dimension called x squared, right? Now all the line actually become the curve, right? Points on the curve. In this case, the red dots and the blue dots, they become perfectly separable. Okay, in this is you can draw a line in this two-dimensional space, they can become separable. So you can prove, right? You can actually prove if you have n data points, if you project your even you have one dimension, okay, if you project it from the dimension from x squared up to x to the power of n, you can make it perfect separable. Okay, you can make it perfect separable. So this is the thing is, as long as you can, if you can project your data to higher dimension space, they can become perfect separable. Okay. Now another case would be like this. You have two features, x1, x2, and then you have two group, right? You have two group. You have in this is a square point and also circle points in there. If you can see, if you want to draw the linear separator, okay, nothing, no matter how hard you draw a linear line in this dimension, you are not going to be able to separate them. However, if you draw a circle, right? If you draw a circle on this, then this circle can perfectly separate these two. Then the question is, how do we define this circle in this way? To define it, what we can do is we can augment. Okay, say our x, the dimension is a and b. So linear separator essentially just be beta 1a plus beta 2b, right? So you can think about a is like x1, b is x2. Now, if we construct the new dimension, which is we can project in this is a and b into this is a 5-dimensional space. You have a b, the original value. You have a times b, a squared plus b and b squared. Now it's a 5-dimensional space. Then in this case, the linear separator, okay, for on this 5-dimensional space, it will become beta 1a plus beta 2b, beta 3ab, right, plus beta 4a squared plus beta 5b squared. This is a linear. This is a linear separator in this 5-dimensional space, right? However, if you're coming back down, if you project it back down to the 2-dimensional space, if you just look at a and b, this is essentially actually define oval shape, right, or ellipsoid shape. This is actually become either not really, it may not be perfect circle, but it could be some like an oval shape, right? It can be oval shape. So of course, circle is one special case. In this case, you can actually find in this way you can actually define this circle non-linear in the lower dimension space, or linear in the higher dimension space, right? You can make your group separable. So this is the power of the so-called nonlinear SVM. Is nonlinear is just basic saying is nonlinear in the lower dimension, okay, in the lower dimension, but it still could be linear in the upper in the higher dimension. Is this clear? Or any question on this? This is a little bit abstract. Well, not abstract. This is example, a pretty concrete example. Okay, so I hope you can, if you look at example, this is points are easy. It's easy for you to see. Any question or anything? No. All right. Now the nonlinear space is or nonlinear SVM. The general idea is the original feature space can always be mapped to some higher dimensional feature space where the training set is separable. Okay. Now, actually, let me back up a little bit. So in this nonlinear classification, okay, our problem is actually our separator is actually this guy. Okay, is actually this guy. Now this separator, okay, this separator as we have in here, if we define in this function here, it actually that means your xi here, original xi is equal to ai bi, right? Now xi star or xi new will become ai bi, ai bi, ai squared, bi squared. Okay. So in the in this in this form, what you're essentially what you're doing, right? In this case is we are defining a new feature vector xi. Okay, the projecting xi to xi star, right? Is a new higher dimension features, and these features can be just plugging into this formula without any issues, right? Without any problem, because then the solution or the including the prediction, again, like I said, is just depending on the inner product between this feature space. So if no matter it's lower dimension or it's higher dimension, then it's the same. Okay, it's the same. So you can solve this is you can solve this is a higher dimension when you have a new feature space. You can solve it using the dual problem, which is like a seamless, right? There's no issue at all. The interpretation wise, okay, if you come back to the original two-dimensional space, now the separator is instead of a linear, you can say it's a linear with this is a 5 dimension. You can also say it's a non-linear with this two-dimension space, right? So that's this is how the non-linear the idea come into play. So is any problem? Okay, so for example, like in this case, we have the red points and blue points. They are separable with this circle, right? With this circle, as you see in the previous slides, we can just project into like this is a 5-dimensional space. It can become perfect separable. Now, is there any like risk or is there any problem associated with this so-called the building up the higher dimensions, the feature space? Is there any like issue associated with it, or is there any problem? Yeah.
Trying to create a linear separator that generalizes wouldn't fit necessarily.
Yeah. So that's exactly the one of the issue is if you try to making two groups to be perfectly separable, okay, that itself is it may create overfitting problem, right? Like I said before, is you have like this example I gave you the last time. You have two lines, right? You have the right. So if you want to perfectly separate it, this is a cross and this is a circle dots from each other. It will be very hard, right? Very hard. And in some cases, maybe they are not separable. Okay, maybe this is just noise. Okay, but if you using nonlinear the separation, you can basically you can probably do something like this. Okay, you can do something like crazy. You can actually, if you project it into higher dimension space and then project it back, this can actually create like a pretty crazy shape in the 2 dimension. Okay, this shape is possible. Okay, don't think this is I'm drawing this like crazy. And like I said, if you project this kind of shape into dimension high enough, okay, in the dimension high enough, they will become perfectly separable. But this separation is it real? Is it like legitimate? You don't know, right? It's possible. It's legitimate. It's in the real world. Maybe you need to separate it, but more likely, this is probably creating like overfitting problem. So therefore, when you project into the higher dimension space, you don't want to project into like too high, right? If you, the more feature you include in there, the higher probability or higher chance of getting overfitting. So this would be the first issue. Second issue is kind of like a little bit minor, but not but it could also be possible is when you're projecting your say 2-dimensional space to a dimension space like with 1 million or infinite space, right? Like a 10 million the space, then it will creating like a more computation. Right? Although I said this is the computing, this is xi trying to xj is not an issue, but if your dimension is become very large, that means your data is become like a huge, right? Particularly if you have a lot of data points. So this is another point is could be the computation. It could be very challenging. So then the question is how do you address it? Okay, how do you address this problem? This problem can be addressed in ways people is called the kernel trick. Okay, the kernel trick. The kernel trick is so the linear. Let me first explain what is a kernel. Okay, then we can come back to the so-called kernel trick. So the linear classifier rely on the inner product between the vector xi transpose xj, right? So this is we define if the original k function is this is the inner product. Now, if every data point is mapped to a higher dimension space via some transformation, is x transformed to hx, right? Just like this transformation, okay? You from this dimension, 2 dimension to 5 dimension, okay? You have some transformation. You can make it say the x become hx. Hx is a higher dimension vector, okay? Is a higher dimension vector. So then the inner product becomes h of x transpose hxj. Now the kernel, okay, the kernel function is some function that corresponding to an inner product into some feature space. Okay, say for example, like in this inner product h of xi transpose xj. Now, if I can write them into some simpler form, say for example, this is going to be equal to e to the power of xi transpose times xj. Okay, I'm just or plus 1. I'm just made it up. Okay. So if I can write in, so there then to calculate this kxj, okay, then there will be 2 ways to do it. One is you can project this xi into hxi project into higher dimension space, the higher dimension vector, do the inner product. You can calculate this xi. Or you can just plug in this xi into this sort of like the form, so the inner product is just equal to this guy. Okay, so then if there's such function, this is going to be making our computational very fast, because instead of you project a higher dimension space, now I can just do an inner product or no dimension space and make a transformation. That's it, right? That's it. Yeah. No, that I'm just giving an example. This could be anything. This is just I'm just saying if you have this case, then this function would be called a kernel function. Okay. So the kernel function basically is a function that can corresponding to an inner product into some like feature space. Okay, that's the inner product. Now, not all the functions are the kernel function. Okay, are the kernel function, because in order to for the kernel function to satisfy, then this kernel function has to be corresponding to some the inner product. Okay, if you have to be written as an inner product of some feature space. Okay, feature space. So but people has proved there are certain group of the functions. This can be written as indeed is the function form, like simple function form, can be written as the inner product of the like higher dimension feature space. Okay, this is an example. For example, we have 2-dimensional vector x. Okay, is x1, x2. If we have in the function defined as 1 plus xi transpose xj squared. Okay, so you can see this function is only is almost as simple as xi transpose xj, right? Because if you compute the xi transpose xj, then computing this function is just plus 1 take the square. So there's almost the computation complexity is almost the same. But we can prove, okay, this form right here can be written as the inner product of 2 dimensions. Okay, you can check that. This can be written as if you augment your features, your x1, x2, if you project into this way, will be 1 x1 squared, that's square root of 2 x1 x2 x2 squared, square root of 2 x1 and the square root of 2 x2. If you can project this x1, x2, your feature x into this is a 1, 2, 3, 4, 5, 6-dimension vector. Okay, 6-dimension vector. Then if you multiply, you make the inner product with 2, it can actually go back to this this function form. Okay, so this is just basic saying in order if I make this a 6-dimensional feature or augmentation. Okay, you build this is x1 x2. I build this is a new feature space as 6 dimension. Okay, when I try to solve the SVM, the algorithm, I don't need to explicitly to do that in the product computation. What I need to do, what I can do is just simply using this as a kernel function to compute this value. Okay, to compute this in the product. So this can make your algorithm really fast. Okay, to make your algorithm really fast, because now you don't need to make the projection and then make it inner product. What you need to do is just to do the inner product original value and then plus 1 square. You can have the value. All right. So is this example clear, or is this the idea? Is this clear? Yeah.
Noting xi and xj as different numbers. Like, why does it go from
here?
xi?
Is xi is representing 1 data points. So this is a feature of the features of the observation I. Okay. Here x1, x2, these are like 2 features. So really, what I should do is a more complex. This should be your vector of xi. This should be xi1. This should be xi2. Okay. So this is xi, xj here. These are 2 vectors. Okay. So this is x here. This is just the feature vector. Right. So yeah, this is a little bit confusing. That's why you can see when we denoting here for the xi, you have in the subscript I in here to denote them. For the j, you have in the j, but when I use the general, I don't have the sort of object number in the subscript. Okay, so this is a simple example. Now, the question is, for an arbitrary function of kxj, like if I write in like my crazy function, right? E to the power of xi transpose xj plus 1 square. Okay. So if I build like any crazy function, this is k of xi, xj. Can this function be written as inner product of some feature space in the higher dimension? Okay, so that's the question. So if you can write an inner product, then that's the kernel, right? So then we can plug in this solution pretty simply. Now, what is the condition which I specify a function kernel which can be written as a product in the product the higher dimension vectors. So if we can prove that, then we can use the kernel function to implicitly map to a new feature space, right? So then this is a kernel function k of xi, xj. Of course, is a favorite real value, and kernel must be equivalent to the inner product in some feature space. Okay. Now, how can we show if I have any kernels, any function, it can be written inner product? Now, the truth is, not all the functions are kernel functions, or not all the functions kernel is kxj can be written as an inner product of the two functions. Now, checking this is the function of xij can be written as an inner product of 2 vector in the higher dimension space can be really difficult. Okay, it can be really difficult. But there's luckily we have a theorem called Mercer's theorem. That's saying every semi-positive definite symmetric function is a kernel. Okay, so semi-positive definite symmetric function corresponding to a semi-positive definite symmetric gram matrix. In other words, if you're having n data points, okay, n data points, you can building up this is a matrix K. This K is defined as k of x1, k of x1, x2. This will be the value you define for like each pair of data points, right? Every pair of data points. So therefore, by building this matrix, you have an n by n matrix. If this n by matrix is semi-positive definite, okay, of course this is symmetric, right? The first function has to be symmetric. Now, as long as this matrix K is semi-positive definite, then this function is a kernel function, okay, can be served as kernel function. But to even verify this is actually not easy, okay, it's not that easy. The people has doing the study and have building a group of the so-called common kernels, like the most useful kernels, has been verified. So these are kernel functions which are quite not, I wouldn't say popular, but these are common used kernels. Okay, this is a linear kernel, which is kernel can be xi xj, right? This is obvious. That's it itself. Any polynomial power p of the xi transpose xj, this is a kernel. Now we show that when the p is equal to 2, we can project it from like a 2-dimension to the 6-dimension, right? And then we can do that. Well, actually, if this is xi is like a 5-dimension the space, okay, this could be even more complicated, but we can we can show that, okay, we can if you have this is a power polynomial power function, you can actually write it as the inner product of two higher dimension vectors. Gaussian kernel, okay, e to the power of negative, this is xi minus xj. This is the L2 norm of square of L2 norm, and the 2 divided by 2 sigma square. 2 sigma square, this is just scalar, right? This is you can see this is similar to so like the Gaussian distribution, right? So that's why it's called Gaussian kernel. This can be written as an inner product of like of the vectors in the higher dimension, or 2-layer perceptron. Okay, this is a function is a tan h or beta xi transpose xj plus beta 1. This can also be written as a kernel function. So for this is a function of what the tan h function, right? Tan h function. This is x. Just to make sure everybody knows it. This function basically is e to the power of x minus e to the power of negative x divided by e to the power of x plus e to the power minus x, right? So this is this is tan x. So if you have in this function, this can also be a kernel function. So that's this is just to when you have in this, right? So when you have this, then basically mean if you plug in this kernel, okay, if you plug in this kernel, like say Gaussian kernel, the Gaussian kernel into here, okay, so K is equal to Gaussian kernel. Now all the things will be same. Then you can have your problem, be written out, and then you can solve your alphas, and then plug in alphas, you can get in your beta. Right, the beta is defined on the orange. Well, actually, you cannot do a beta, right? Because the beta, there's no beta. Essentially, in this case, is if you're using the K, you don't have beta, but you don't care, right? Because what you need to do is do this the prediction. So your prediction is now we still need to B, right? B can be calculated because B, as long as you identify this alpha, if it's not a support, is as long as it's a support vector, right? Alpha I is bigger than 0, is not non-zero alpha I, then alpha k, so we can find out its value and also its slack value. This two is there, and then we can plug in. Then we can do is just plug in this kernel of this function of xi and sk, right? So we can as long as define the kernel function. We can solve the alpha. We can calculate the value of b. Then we can also make our prediction. If a new points come in, I can just plug in my kernel. I know which classes this is going to be the classified. So you can see there's in here. If you plug in this is a Gaussian function. I don't even need to know what corresponding the higher dimension vector is. Right? I don't need to know that because this is just saying that implicitly, okay, implicitly there will be some. This can be written as this can be written in this form. Okay, implicitly this can be written in this form, but I don't really know what exactly this H is. Okay, this is a projection. How the projection is done, I don't know. Okay, I don't know. So this is kind of like a and this structure is very important. Okay, because this structure is where you can prevent, well, not prevent, is kind of like mitigate the overfitting issue. Okay, because all the overfitting is coming from unstructured of the data structure, data form, or the model. In other words, the simpler your model is, then the less chance you have real overfitting. This is why, like a linear model, just a linear line, right? The linear model, that means your points have to follow a linear line. That linear line itself is a structure of your model. So this kernel is kind of like putting the structure to your higher dimension space. Okay, so you can project in your features to like higher infinite space, but that's infinite space. They have a structure. Okay, and that structure is captured by this kernel, by this mathematical form. Okay, so this is the form itself. Okay, can sort of like can give in as a little bit like the putting a structure to the model, which is giving us less chance on the overfitting. So this is kind of the generation from to the nonlinear problem. Now SVM was originally proposed in 1992, and it really become popular. And this is SVM itself. Okay, has been applied to many different applications, and these are the this is just this is not a full list, right? This is just some examples. You can see as long as you can formulate the problem into this is into the SVM, this is a problem. The form they can be used very widely in different fields. So the good news is we have the same program, same algorithm, with a new kernel. Then we have a new SVM method. So this is why at the beginning I said SVM is not a method. Okay, it's a class of method. This is why because you build a framework and you plug a new kernel, you already have a new SVM, and no problem with the local minimum, few model parameters, robust optimization method, and with the successful application. Now there are still some issues are still unaddressed. Okay, for example, how do you choose C in the your maximization? Like here, what is the C? Okay, we kind of like wave our hand, we didn't pay attention to it, but in practice you have to have in the C to be classified, right? C is kind of like, again, is like the hyperparameter you have to decide, and which kernel to use. Right, so we have so many kernels, right? So which kernel to use? That's a question you need to have to. This is have to done using like try and error methods. How do you interpret the results? Because now when you have in the kernel, say the Gaussian kernel, I mean, what's the interpretation for the results? How do you have a feature and you have in the prediction? How do you interpret the results? And how do you handle categorical variables? Right, because now all the method I have now is X is kind of, I assume, is continuous. But if you have categorical variable, how do you handle them? All those problems, these are legitimate questions. Okay, where if you want to study like more SVM, these are things you should go checking down the road. You kind of a little bit more learn a little more about SVM. But that's not focus of this class. What we want to see is how can we making this SVM scale to massive data set. Okay, that's this is sort of like what we want to address. Now, for this is a SVM, like using the kernel function, like the user say Gaussian kernel, can that Gaussian kernel SVM be used in the big data? Like, is that easy to do? Is if you want to apply into the into this using like say ADML method to apply it, right? Is that easy to do? It's actually hard, right? If you're using Gaussian kernel, it's actually hard. Why is hard? Because if you want to use ADMM, how we do that? ADMM assume we are solving the model locally with each data partition, right? So therefore, each model it will having a local parameter. And then we assume you have a consensus parameter, right? We set in local parameter equal to constraint, local parameter equal to the global, like consensus parameter. So then we iteratively solve that. And now, if you're using Gaussian the kernel, we even skip this beta step. We jump directly to the prediction, right? So therefore, we don't really have a model in these cases so what is local model? We don't have even beta. Now, then to apply the SVM into the large data, to the big data, we have to step back a little bit, okay? Step back a little bit is we need to have in some sort of the separator can be written as explicitly within some kind of parameterize. Okay, you have to explicitly parameterize our model. So in this case, we can in another way we have to explicitly construct a high dimension vector, say HXI, right? We have built a vector. Then associated with this vector is a bunch of this beta. You are having a beta, right? The beta is your parameter. So then within this beta, we can apply our ADMM to it, because then you have a local model. Each model you have in the beta I or beta k to it, right? It's going to be specified to each part of data, and then you globally we can sort like to constrain them within the consensus the beta. No, but this is also creating a little bit of problem is I still having this is a constraint, and I still have these constraints to take care of. And these constraints, although it's specified for each data point, which means they're local. Okay, we can specify. But the more interesting way to do it, I'm going to show you another way to do it. It's kind of more intuitive. We can actually see this is it actually can be more to me. I think it's more, if you see that it's actually more intuitive. In other words, the problem above, okay, this is our primary problem. This problem can actually reformulate it in as a problem down below. Okay, the problem down below basically it says the phi beta equal to lambda is summation I from 1 to n 1 minus yi of f xi. This is plus this is a function. Okay, this is a function which is defined as this. This is a function where it's called Abel function. This is called Abel function. Abel function. This is essentially is given by this. Okay, so if we define this is x, this is y I of f x I fx. Let's do not use I here. Then this function basic saying if you yi times xi is bigger than 1, it will be just if it's less than 0, it's going to be 0, and if it's positive, then it's positive, which means if this function right here, okay, this function, if we define this as 1 minus y of fx plus, okay, this function is basically saying y times fx is bigger than 1, then it's become negative. Then it's negative, then its value is going to be 0. And if it's less than 1, it's positive. It's positive just be itself. Okay, so this is called the positive sign. So in terms of this is the function, it can be written like this. So you can see this look like an apple, right? So therefore, this is a function also called hinge loss. Okay, it's like a it's like a hinge, right? This is like an apple. So this function form is called hinge loss. So basically, I'm saying this problem above can be reformulated as a problem which is saying I have a hinge loss on every subject. Okay, I have a loss function for everybody, then plus some kind of penalty. This penalty is like L2 penalization, right? So then this will be essentially is summation I from 1 to n of some loss function of xi, yi, plus lambda of beta squared, L2 of the beta. Now, if you write it like this, then this essentially is what? Then this is no different to solving the logistic regression, right? This is logistic regression, just change a different loss function, right? What I'm using here is a hinge loss. Logistic regression is just using the loss function for the logistic. Basically, is a negative log likelihood, right? So it's the same. Then we know how to handle the penalization term, right? We know this. So if you can write in the above form, the above form is kind of like you have in this function, you have the constraint is not the form you're familiar with. But if I write in the form down below, this would be the ones you already work with. The question is, how do we do that? This actually can be, so let's look at this constraint, okay? Let's look at this constraint. First of all, we have the psi I is bigger than or equal to 0, right? So this part is no problem. So this is psi I. If you look at this case, now we can divide this into three conditions, okay? So first, if one minus yi of fxi is less than 0. So from here, from the equation here, okay, we know psi I, it has to be bigger than or equal to 1 minus yi times fxi, right? We just, if I rearrange this inequality, I can see psi is bigger than 1 minus yi times fxi, right? That's no problem. Now, if in the cases where 1 minus yi times fxi is less than 0, then given within the second equality, the psi has to be bigger than or equal to 0. And at the same time, we want to minimize the psi I. So what the psi I value should be? Psi I has to be equal to 0. Right? So for the points, if 1 minus y of fxi, we know is first thing, then this, if 1 minus y actually less than 0, then this equality automatically satisfied. Right? And then the psi bigger than or equal to 0, and we want to minimize it. So therefore, psi has to be equal to 0, right? This is the first case. Second case, if this is a 1 minus yi of xi equal to 0, okay? In this case, psi I, the same argument, psi I has to be equal to 0, right? But then these two are the same. You want to minimize psi, so psi equal to 0. Now the third case, okay, is the third case. If 1 minus yi of fxi is bigger than 0, so what's the psi should be? Then in these cases, then this second psi bigger than 0 become inactive, right? Become inactive because this is bigger than 0, right? This is bigger than 0. So the minimum psi is going to be equal to 1 minus yi of fxi. So taking all the three arguments together, okay, we can say what is psi I value should be. Psi I essentially should be 1 minus yi of fxi, the positive part, right? Because if it's less than or equal to 0, then psi equal to 0. If it's bigger than 0, psi will be equal to value. So therefore, psi is equal to this guy. If we plug it in, okay, if you plug it in here, so then the first term right here is basically summation of the psi I, okay? The second term, this is a beta transpose beta is essentially this term right here, okay? So and all this equality down below, this has been already automatically satisfied, okay? Because we don't need this constraint anymore because it's already been absorbed into this hinge loss. So therefore, by combining these two together, you can see we can rewrite this form into the form down below, okay? With the hinge loss and plus the L2 penalty, okay? This is what it says. Okay, is this clear? Now the one thing left is this is C, okay? This is C. I just divide this C by both sides because C is just a constant, okay? Divided C on the both sides, then this lambda essentially is just 1/2C, right? This is just reparameterize everything. So yeah, if I divide C, remove this. This is the same problem. Okay, same C is just constant, doesn't play any role. So you can say if I rewrite this in this form, then this will be in a form where we can apply ADMM algorithm, right? Because now you have a local problem to solve within the beta I, and then you can constrain within the global beta, the consensus parameter beta to there. So then you can have that. Okay, any question on this? Is this clear, or is this everybody follow? All right, so if you kind of you need a little bit thinking, okay, a little bit thinking to get this to make this right. So if you kind of like didn't kind of follow, you can go back to review it because this is recorded. All right. Now let me finish this class. So therefore we have a consensus. This is called consensus SVM. So you have a loss function which is defined by this with L2 regularization. This is our problem, right? So then we have a global problem. Then can be written, you have the data n data partition. Each one of beta I will be its local parameter subject to beta I equal to beta. So therefore we can plug in this into ADMM. So the local SVM basically is we have beta I. We can minimize this function, right? So this is just this will be exactly the same ADMM algorithm you've seen before. So we can update the consensus, we can update the beta, and then we can distribute the beta back to the locally, update the mu, update u, which is the Lagrange multiplier, and then back and forth. Okay, so this is how it works. I'm not gonna go through this detail because this is just the same ADMM implementation. So once you get into this, once I get to this point, okay, to apply to ADMM should be easy. So the toy example in this case is just to see if you apply to data points like 400 data points, we divide it in 20 groups. Then this will be in the first iteration. This will be like if you do a linear separator at the first beginning, the black line is a ground truth. Then for each group, you're gonna at the beginning you can see you do the random the partition, the line is all over the place. But as the iteration goes through, okay, your line actually converts. At the iteration 40s, it actually converts pretty well to the like ground truth, the global maximization. Okay. Okay, so this is all for the SVM. I want to say. Then in the next Monday, we're gonna have the last lecture. What I'm going to do is introduce like probably a little fast introduce the random forest. Okay, so that'll be all. So just a reminder, okay, because this is some people join late. Final exam, the time is December 10th. It's a Wednesday, 11:15 to 1:45. Location is Java's lecture hall 101. Okay, make sure you know the place. Okay, sometimes it's a little bit harder to find the Java's. Make sure you go to the right place. All right, that's all for today. I'll see you guys next Monday.